Okay, before I go on, let's talk about the periodic table and valence electrons. I'm going to show you how to use Lewis dot structures, but I first need you to take what we just learned about ionic compounds and put that aside in the ionic pile. And now I'm going to teach you how to deal with things from the covalent pile. Covalent electrons don't usually have metals in them, so you don't have to worry about this much of the periodic table. Also, we need to consider hydrogen can be over here in some ways, counted over there, and it can be over here in other ways, counted over here. Because it's so small, it kind of just does weird things. Covalent compounds are two nonmetals. We're talking just right up here. Okay, maybe a little bit down there. Okay, that's it. When we look at Lewis dot structures, the first thing that we're going to do is count the number of valence electrons. Now remember, valence electrons is how many electrons you have on your outermost shell. So chlorine might have 17 electrons normally, and we're not talking about anything charged, we're just saying chlorine. Okay. Now we're going to count how many valence electrons it has outside of just that neon. We can do 17 minus 10, or let me show you another pattern from the periodic table. 1 valence electron, 2, 3, 4, 5, 6, 7. That's all we're doing, we're counting to 7. So when you count the number of valence electrons, you need to count how many each one has. Carbon would have 1, 2, 3, 4, nitrogen would have 5, oxygen 6, fluorine, chlorine, bromine 7. Okay, so we're going to start trying to put together covalent compounds, and by we I mean you. Okay, so here's what we're going to do. We're going to start by counting the number of valence electrons in a given formula for all the atoms, and don't worry about what I said about charges here, okay? You start by putting the odd man out, or the one that's like the only one in the center. We're going to get past that pretty quickly, but that's the easiest way to start if you're not sure where to start. Most atoms should have 8 electrons. We call that the Octet Rule. We've talked about that before, and the reason why is because everybody's trying to be like a noble gas. So instead of gaining or throwing away electrons and getting them back, covalent bonds share them like this, and they basically try to figure out a way to get to 8 electrons in their outermost shell. Yeah. This is a covalent bond like what you see down here. Those 2 dots represent a bond. So I'm going to show you this from the beginning. The only exception, by the way, the big exception here in the beginning, hydrogen, right here, wants to be like helium. He only needs 2 electrons. He's not big enough to have 8. Okay? So let's start by looking at CH4. Carbon has 4 electrons, or 4 valence electrons. And I got that by counting 1, 2, 3, 4. Okay? Hydrogen has 1. There are 4 hydrogens here. That's what that subscript thing means with a 4. 4 hydrogens at 1, so that's 4, plus the 4 of carbon, total of 8 electrons. So I put the odd man out, the carbon in the middle, and I put hydrogens north, east, south, west on that carbon. And I just put 2 dots in each of those positions. What those 2 dots represent is a bond, or a holding of hands between that carbon and that hydrogen. Okay, so that's where they're going like this. Anything that exists between these two counts for both of them. So this hydrogen gets 2, and at the same time this carbon gets these 2. So here I have 2, 4, 6, 8 for carbon, which is what he wants, yay. And I have 2 for each of the hydrogen. Fantastic. Now let's look at NH3. NH3, nitrogen, is going to have 1, 2, 3, 4, 5 electrons, valence electrons. So nitrogen has 5, and there's 3 here from that hydrogen, so I'm adding those together to get 8. This is how many electrons I have to put together everything, okay? I can't use more than that or less. Nitrogen, therefore, I'm going to put in the middle, 3 hydrogens surround him. It makes no difference, that's what this note is saying. It makes no difference if you have the hydrogens this way, that way, it doesn't matter. They're all the same thing because in truth these are floating around in 3D and changing all the time anyway. So here we have nitrogen with 3 of them around it, and each hydrogen has 2, nitrogen has 8. This nitrogen right here with 2 electrons, these are called a lone pair. So these stick by themselves. They're not connected to anything, but they're required for nitrogen to have its octet. Okay, let's get to a harder one. Here we have NF3. Nitrogen has 5 valence electrons, just as we counted before. So 1, 2, 3, 4, 5. If I keep going to fluorine, it's 6, 7. Okay, so let's count the number of valence electrons. There are 5 in nitrogen. Excuse me. Fluorine has 7, but there's 3 of them, so 7 times 3 is 21. Add those together, you get 26. That's how we put this guy together. Okay. That means that we have nitrogen right here, fluorine goes around him, and then we start putting dots. So first I put 8 around nitrogen, and then I just keep going. This is easy then, right? Okay, I'm going to do another example. Let me grab a piece of paper. What if we did PCl3? Let's see. Phosphorus would be 1, 2, 3, 4, 5, right? And chlorine is 6, 7. So we have 5 from the phosphorus plus 3, that's where that comes from, times 7 from the chlorine. And that's again going to give us 26 total electrons. So I put phosphorus in the middle, and I put chlorine around him. Just for giggles, I'll put him up there, okay? And I start putting electrons around phosphorus, and then around chlorine. That. Now let's count and make sure that that's 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6. Everything's happy. Great. We're good. Until we get to something with a double bond in it. That might be a little bit more difficult. So let's count up the valence electrons in CO2. So first we look at carbon. Carbon has 1, 2, 3, 4 valence electrons. Oxygen has 1, 2, 3, 4, 5, 6. So let's see. Carbon has 4, oxygen has 6, but there's 2 of them. Total number 16. I've got it here for you in notes, but I'm going to take it over here. CO2. So we have 16 electrons to put this together with. So you might start with carbon, oxygen, oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. See how that's a problem? When you have too many of something, that means that usually we need to do something like this. I'm going to cancel these 2 out and move them inside. What this means is that I have a C double bond to oxygen. So there's 2 bonds between those, and they share all of these guys inside. Okay. Now this oxygen has 1, 2, 3, 4 pairs, or 2, 4, 6, 8 electrons is a better way to say that, sorry. Carbon has 2, 4, 6, 8. And oxygen has 2, 4, 6, 8. It's happy, right? Let's make sure we have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's another problem, right? So this time I'm going to say, I'm going to get rid of these, and I'm going to put them between here and see if we can share that way. Okay, so let me rewrite this now. It does not matter which direction you put those lone pair of electrons. I'll keep them consistent to make it look prettier. Okay. Now let's count. We've got 8 around this oxygen, 2, 4, 6, 8. Carbon has 2, 4, 6, 8. And oxygen has 2, 4, 6, 8. We're good. Now let's count, make sure we have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. This is the right structure right here. Another way to draw that would be like that. So carbon is 2 bonds to both oxygens. Okay.